Cylindrical cost evaluation, grinding versus hard turning, is for anyone that has a need to understand the cost advantages or disadvantages for grinding versus hard turning. The potential users are engineers, salespersons, manufacturing managers, and cost estimators. Because of the nature of the input and calculations, this program can be used for comparing any grinding wheel regardless of specification and any turning tool regardless of material. This is the only product I have that has two different inputs, one for inch and one for metric. All the other products allow for the user to choose in one program between inch and metric. I will have this changed in the near future. For this presentation, I have chosen inch, and if you had chosen metric, all the terminology would have been in metric. Making a decision for turning versus grinding depends on a lot more than just the calculations from this program. Considerations include production numbers, tolerances in both size and surface finish, machines available, just to name a few. The program is divided into 6 sheets, 5 of which are interactive. The first, titled Instruction, and is written instructions for this program. Let you look at that, and is accessible from the first sheet titled Input Grinding. We will start on this sheet and move through each discussing the input and how it works. The top section is broken into 2 sections. The top section is the general input that's used interactively with all the sheets. Our first choice is whether we're going to be doing an OD or an ID. I've chosen OD. Remember, all the blue font cells are the ones that are musts as far as input. Any of the black or black font cells are optional. The next potential input it's important is wheel diameter. We have chosen 20 inches. This is, of course, the grinding section. The wheel width is 2 inches. The wheel to part contact is 2 inches. The usable depth of the wheel is 0.5 or a half inch depth. The wheel RPM is 1600. The jet dresser type that we have chosen for this application, we had a choice of single point, rotary straight, or rotary plunge. We chose rotary straight. The next 3 or 4 are very critical because the dressing input is what's going to tell us what the wheel life will be relative to this particular part of the application. We show the dresser end feet of 2 10,000ths, number of passes per dress 2, traverse rate in inches per minute at 6,500, or 6.5, excuse me. Number of parts per dress 50. The rotary RPM is 6,400, and the rotary diameter in this case is 4 inches. Now the CBN insert for this demonstration or for this process is $38.40 customer net. The time period, we have a choice of day, week, month, or year. I've chosen year. And the next important input will be the machine time in seconds. Now this is the amount of time that's not involved in the grinding process or in the turning process. This is the time where you're doing movement through air, moving the machine from part to part, whatever. For this I've chosen 20 seconds. The wheel change time for this grinding wheel is 1 hour. The wheel cost each is $5,000. So for this process I have chosen CBN wheel, and in fact the turning is going to be comparing PCBN for hard turning. The total labor and burden cost or rate is very important and can range almost any number. I've seen it as low as $25 and as high as $121 plus. For this application we have chosen $85 per hour. The number of parts per time period, we have inputted 85,000 for the year. The number of shifts, we have a choice of a half a shift, 1 shift a day, 2 shifts, or 3. I've chosen 2. So now this has been, the top end is input and finished, and the bottom half will be strictly for your grinding process, and it is interactive only on the grinding process sheet. The first most critical is the entry for all applications is diameter width, and part RPM of each diameter that we're looking at running. In this particular case, we have chosen 4 diameters, 2-inch, 3-inch, one is slightly larger at 3.05, and 1.5. The width on the first part or section is 0.750. The next 2 sections are both 3.750, and the last section, diameter 4, is 1 inch. Part RPMs for each application is 160, 107, 107, and 213. The next section is the plunge in-feed rates. Now we could have eliminated all of this and going straight to a traverse grind similar to what you would be doing in turning. In that case, none of these numbers would be input, and the traverse grind would show all 4 diameters, and then you would be looking at your traverse rate inch per minute, your part RPM, stock removal per pass, number of traverse passes. As you've seen, we've chosen 15 thousandths as the radial stock amount. So we would, if feeding at 1,000 per pass, we would have to have 15 traverse passes, and then of course the number of spark out passes. In this case, we're going to do all in plunge and then only traverse, which we highly recommended, those widths, those diameters with the width is larger than the width of contact of the grinding wheel. If you remember, we input the wheel to part contact above at 2 inches, and diameter 2 and diameter 3 have a width of 3.750 inches. Therefore, the program will calculate how many plunge grinds we need to make, and then those 2 diameters only will be traversed, and that those need to be the ones you input so that the program knows how much time it will take to travel the 2-inch wheel across those 3.750 parts. So let's start with the plunge grind. We are looking at a radial in-feed to 0 of 15 thousandths from the rough position to finish. We have already input a machine time, which will include any rapid feed or air. So if your machine is set up, for example, on diameter, then we would need to divide that by 2 to get a number for the radial stock to 0. I know that the stock can range, but we need to put in an average, which would be a good average, so we're going to start with a known number of 15 thousandths. Then from the rough to the semi-finish. Now, I want to let you know that this could be different nomenclature, not necessarily rough, semi-finish, finish, and micro. It could be anything, but all we have is 4 in-feed numbers. So the first, what we're calling rough, down to the semi-finish, which would be the second plunge, is a total of 5 thousandths. We're going from 15 thousandths down to 10 thousandths, which is where we come up with the 5 thousandths. The next move would be from 10 thousandths down to 2 thousandths. So we would have a total stock removal on radial of 8 thousandths, and that's where the in-feed rates would be calculated from. And we go to micro of 5 tenths, which means we'd have a total stock of 1.5 thousandths, and the final feed would be the total left of 5 tenths. I've chosen the in-feeds for each diameter. As you can see, the first rough will be at 79 thousandths for the diameter 1, and so forth as we go down the list of diameters. And I've added a second in between the rough feed and the semi-finish feed as a spark out. You don't need to do this, and would probably not been in a normal CBN process, but I did add it for a reason. We'll get to that later. The next level, I've kept them the same. Also left another 1 second between the two, and then you can see we start seeing a change in the in-feed rate. We've gone from 79 thousandths to 40 thousandths and maintained that through the grind. Skipped over spark out between finish and micro, and left 5 seconds each for each diameter at the end. For the traverse grind, again, remember, we're only using number 2 and number 3, so we skip number 1, skip number 4, and we just add the information for feed rates into diameter 2 and 3. Those are the diameters, as we discussed, that have the wide section, a section wider than the wheel contact point. For this, we're running 50 inches a minute for both, 122 RPM. We're taking a total for this of 5/10 just to get the lines out, and we're making one pass, no spark out pass. Also for this demonstration, I left a face to grind, and that would be a face between the two journals, the diameter 1, 2 inch, and the diameter 2 a 3 inch. The RPM is higher than 3. It should have been 107. We're running 24,000 inches per minute. We have a 3-second spark out, and we have a total in feet of 5 thousandths. Now we're finished. We can move on to the input for the CBN. Now, again, all the blue fonts are the inputs that are important. The insert type, the insert radius, the insert grade really are not that important, or insert edge prep, for the calculations at all. But they are important if you're looking at another company or a company to supply you a competing or some insert to compete against the grinding process. So that's why I've entered these in blue. The two most critical on this far left and must be input are the number of parts per corner. In this case we have 50, and the number of corners per insert, which is 2. So this has already been established that we get 50 parts per corner and we have 2 corners per insert. The rest in the middle are NA, or in my first one, coolant dry, because we aren't going to be using coolant. But again, this is data that's not critical for calculation, but for information data. The diameters, we have up to 10, as we have in all these processes, but we're only using 4. And that's been brought over from our first input, the 2, 3, the 3.05, and the 1.5. Now we need to know what the average face diameter and length is. So if we took the 3 and the 2, added them and divided it, we know we have a 2.5 inch average face diameter. And that the length, we go between the 2 and the 3, which is 1 divided by 2, we have a 1/2 inch face length for the insert to turn. The machining time, we're using exactly the same. It may be different, but for this demonstration, I'm using the 20 seconds. But whatever it would be for your lathe, that would be the input. The number of parts per time period are the same. We still have to do 85,000. The insert cost per each is brought over from the earlier input. And the time for changing inserts, I put down 30 seconds or 1/2 minute. Now, since we're doing faces, and even though we've added face information at the top, we still need to put in what the surface footage of that part will be turning, the in-feed rate, or IPR, inches per rev, and the total in-feed, or for the process. And this is going to be the same as we had before, of 5 thousandths. Because we put in the surface foot, it does calculate out that that means we'll be running at an RPM of 611. Then the traverse data is we're going to be running on all 4 parts 8 thousandths inches per revolution. That will be your traverse rate. The surface foot per minute is always going to be, or at this point, all going to be 400. Could be anything, could be different, depending on your input. Your stock removal, I've just kept the same, which is what we had originally for the grinding. And the number of traverse passes is 1. And now that means we filled out both the grinding side and the input for the CBN insert side. So now we go to the CBN wheel. The top end, or top left side, and over to the right a little bit, are all the input data that we input in the first sheet. There's very little calculations other than, for example, the wheel RPM is 1600. We've calculated that the grinding wheel is running at 8,378 surface foot, and that we have 6,700 on the surface foot of the rotary, which has given us a 0.8 roll to wheel ratio. At the top, you can see we have the diameters we had input, the 2, the 3, the 305, and 1.5. The different widths are the same. The plunge RPMs that we had entered. And that gives us the surface foot based on the RPM and the diameter of the part of 84, 84, 85, 84, which calculates almost to a 100-to-1 ratio between the wheel and the work. We move down to the traverse grinding, and again, traverse grinding was, we skipped diameter 1, and only we're doing the 2 diameters that were wider than the wheel face, number 2 and number 3. The input data is the same, RPM's the same, amount of stock, number of passes, and it calculates out that we're running at 20% the wheel width per rotation of the part, and the cycle time is 9 seconds. For face grinding, again, we bring over the 24, the 3 on the spark out, the total in-feed. In-feed rate per rev is at 8 thousandths, which we saw, and the cycle time is 15.5. Now the plunge rates are going to be, again, the 15 to the 10, which comes out to 5, 10 to the 2, which is 8, microfeed 5 to 0. All the in-feed rates are duplicated from our original input, what those cycle times would be, and what the cubic inch per inch minute, or Q prime, would be. And then we get a total calculation. Dressing time parts per second, what the total grind cycle time is, which would be 2.42 minutes, total grinding floor to floor, machine time loading, projected wheel life, is based on the input of the number of dresses and how much we're dressing each one. Time to change a wheel, 1 hour. The number of parts entered per part period is 85 grand to 85,000, and this particular, based on production, could do 90,071 per year, or 0.9 machines per year. Wheel cost at $5,000. The projected number of wheels used in that period is only 1.4. The hours were changed at 1.4. The cost of wheel changes, lost production, $115. We move on down and see that the total labor and burden plus wheel cost is $3.98 each. We move over to the insert, and by the way, this is totally locked out, as are all 3 of the last sheets. Now we move to the insert page. Again, all the data has been brought over. Again, you can see the same numbers, what we're feeding, and what the surface foot is. Then we have the turning diameter. So this is giving us all 4, what the cycle times are per part. You can see these are longer because the part length is longer, or width. We have a total of 126 seconds total cycle time for the turning process of the diameters. Doing the face, we only have 1 face. Total cycle time for that, based on our input, is 6.1, which computes out to 6 of round off. And then we have the same data as we saw at the beginning. We have 85,000 parts time period. We can do 97,474, which should be about the same, a little bit more, 90,000 for the other. But that still computes out to about 1 machine to do the part. Total cycle time, 2.5 minutes as compared to 2.75 minutes. I think that's right, 2.5 to 2.75. So in fact, the hard turning is a quicker process. But as we move down in this, and I've made this, please understand, I've just made this so everything would come out very even. There's a slight advantage for the grinding, but this was the total, the process was just set up to show as a demonstration. But a number of parts we go down, we'll see that the biggest cost difference is the cost of insert per time period is now 32,640 versus the grinding wheel, which was 5,000, or excuse me, 115. So the cost for the edge to change the parts, 616. The total burden and labor cost was 398. So we go from 398 versus 342, and we save a total of 113.50 for grinding. So we see a loss, because in this case, always the turning is the dominant. So red means a loss for the turning, black means a positive for the turning, and vice versa. We go to the synopsis calculator, you can see this even better, CVN grinding versus CVN turning. And in fact, everything is pretty even, since we're really looking at a toss-up between the two. All downloads for sale on www.com AdMart site are packaged in zip files. When you download after purchasing, please remember to extract all when opening the file, or you will not be able to listen to the packaged audio. In all cases, when you purchase any product, you have a number of downloads available from the site in case you have an accident or lose the file. I will be adding to the list of products in time, but for now you will have to find 8 distinct products, including this product, that you could find helpful. Also, you will find interactive software that is listed under engineering software and has its own location on the website. This is for sale as a subscription and can be purchased with a 1-year renewable subscription or shorter time periods without renewable subscriptions. I set up this example to show how the cost examples relative to two processes, turning versus grinding. If you have any questions, please do not hesitate to contact me, Dale Savington, from the Contact Us on our webpage at www.admart.com.